Good morning. My name is Isabelle Guyon, and it is a pleasure to present to you today, in the name of the AutoDL Challenge team, the design and the results of the Automated Deep Learning Challenge. I would like first to thank the organizers for inviting me. The organizers include Frank Hutter, whom you can see on this picture with me, at a time when conferences were not yet virtual. And I would like to thank all my collaborators, who include as lead organizers Olivier Bousquet, André Elisseff, Zhenging Yu, and Weiwei Tu, and as core team members, Sergio Escalera, Julio Jacques, Messan Madani, Adrien Pavao, Sébastien Treger, and Zheng Su, as well as many other people who contributed to the starting kit, the datasets, and the challenge platform. Finally, I would like to thank our sponsors, home institutions, and the conferences that hosted our events. So, where do we come from? We are a team of people interested in automated machine learning, or AutoML. We pursue the ideal that we want to build the perfect AutoML black box to which you input some training data and, without human intervention whatsoever, produces a trained model ready to use. As we all know, it is difficult to make this dream come true. But this is what inspired us to start a first series of challenges on AutoML limited to tabular data. And lo and behold, Frank and his team at AAD Freiburg produced a Python-based tool called AutoScaler that not only won many of these phases of the challenge, but became a standard in the field to automate machine learning for tabular data. AutoScaler is a wrapper around the scikit-learn library that does both model and hyperparameter selection for you. But then we wanted to go beyond tabular data and venture into applications for which deep learning dominates today's state of the art. And as you know, deep learning methods have many adjustable hyperparameters, and the day has not come yet when skilled data scientists are no longer needed in applications to design good architectures and select hyperparameter settings. But with the help of dozens of researcher teams around the world, we have ventured in trying to squash the need of human intervention and move towards automated deep learning, with the additional constraint that we want fixed time, fixed resources, raw data, multiple modalities, and all that without any human intervention whatsoever. To attain this goal, how did we design our challenge? Well, first, with a lot of graduate student sweat. We started in 2017 with the initial impulse of Olivier Bousquet and André Elisseff at Google Zurich. You can see me on the left doing some tourism at this occasion already in 2017 in Switzerland with my grad student Li Sheng, and at the bottom the following year with my second grad student Zhenging Yu. Then, such challenges need a lot of data. We enrolled the help of many people to donate data with a variety of modalities, images, video, speech, text, tabular data. And we are grateful to Adrien Pavao, who formatted the majority of them in a common TF record format designed by André Elisseff. In total, we reached more than 100 datasets, 61 of which ended up in the challenges of the AutoDL series. All tasks are multi-label classification tasks. On this slide, you can appreciate the diversity of datasets in terms of number of samples and compressed size. Each point represents one dataset, and the color represents various modalities considered: image, video, speech, text, and tabular data. Image, video, speech datasets are the largest in terms of compressed data, while text datasets are the largest in terms of number of examples. We provided raw data, but formatted in a uniform tensor manner, meaning that the samples of regular feature-based datasets were vectors, that is matrix or tensors of dimension x111. Grayscale images were 2D pixel matrices or tensors of dimension xy11. Likewise, we encoded color images as tensors of dimension xyz1, where z is the color channel for speech, text, and video, we added an extra time dimension. All original samples were not necessarily of the same size, so we added zero padding to make all tensors the same dimension in the formatted data. We quickly realized that introducing right away all modalities in a challenge would be too hard, both for us and for the participants, so we created a series of challenges, introducing one modality at a time, culminating in the NeurIPS 2020 AutoDL challenge, which had all modalities. The AutoDL challenge series was with code submission. The participants had to submit code capable of handling both the training and testing. Since the code was run on our challenge platform, for practical reasons, we limited the evaluation time to capital T equals 20 minutes per dataset. Our evaluation metric was the area under the learning curve, or ALC. The learning curve is a plot of a performance score S, which we chose to be the area under the ROC curve, as a function of time. The ALC is the area under that curve, or the integral of S. Using the ALC as a metric allows us to continuously monitor progress of an algorithm during training. This imposed on the code of the participants to save immediate predictions on test data, and this put pressure on the participants to work on anytime learning, that is, to deliver methods which can be stopped early and yet provide results as good as possible. To adjust the relative importance of the beginning and the end of the learning curve, we normalized the time axis, and we have an adjustable parameter t0 in the definition of t tilde. Introducing t0 allows us to reweigh the importance of the beginning of the learning curve. We fixed the parameter t0 to 300 during the challenge, and we will see in our later analysis that results are rather insensitive to changes in t0. The code of the participants was fully blind tested. Each challenge had two phases, one feedback phase, during which methods were trained and tested on the platform, on 5 practice datasets. During the feedback phase, the participants could make several submissions per day and get immediate feedback on the leaderboard. The feedback phase lasted 1 to 4 months depending on the challenge. Obviously, since they made so many submissions, the participants could, to some extent, get used to the feedback datasets. So for that reason, a final ranking was done in a final test phase on 5 fresh datasets. One final code submission only was allowed in that phase. Since this was a completely blind evaluation, during both phases we provided additional public datasets for practice purposes and to encourage meta-learning. To illustrate how submissions must be formatted and get the participants started, we provided a starting kit. In all challenges, we provided at least 3 baselines. 0 is constant prediction, 1 is linear model, 3 is multidimensional CNN with auto-rescaling. In the last AutoDL challenge, we also provided baseline 3, which is a combination of some of the best methods entered in the previous challenges. This also allowed us to check ahead of time that our datasets were properly formatted and the tasks were feasible. We ran the challenge on the CodaLab platform, which is an open source project of which we are community lead. CodaLab is free for use for all. We used to run the calculations a generous donation of Google of 100,000 cloud units. We prepared a Docker, including many machine learning toolkits and scientific programming utilities, such as TensorFlow, PyTorch, and scikit-learn. We ran the jobs of the participants in virtual machines equipped with NVIDIA Tesla P100 GPUs. One VM was entirely dedicated to the job of one participant during its execution. To recap, our challenge design included raw data from 5 modalities: image, video, speech, text, and tabular data. We imposed a fixed time budget, anytime learning through the ALC metric, and blind testing. We provided a starting kit, sample public data, and baselines. And we also provided fixed computational resources identical for each participant. And finally, we did not impose that deep learning should be used. So what are the challenge results? And now who won? We would like to warmly congratulate the winners. As you can see, some teams are serial winners. Other teams could not participate to all challenges and abandoned the race, but since their initial solution was open source, it could inspire others. This is the case, for instance, of the computer vision star Cacao Brain. The final overall winner is Deep Wisdom. They provided a robust and reliable solution that ran without failure on all 10 datasets of the AutoDL final phase, which included 2 examples of each of the 5 modalities. But really, everybody won in some sense, because we have learned so much in the process. This table shows that the number of participants was moderate compared to other challenges we organized, which attracted thousands of participants. This is not so surprising, since participating involved a fair amount of engineering, and off-the-shelf solutions could not be used. Still, hundreds of participants gave it a try, and in the final AutoDL challenge, we had 54 participating teams, 247 overall submissions, and 2,614 dataset-wise submissions. In the end, 8 teams made it to the final line and made valid final submissions. For most datasets, the top teams improved significantly over baseline 3. The performances were averaged over several runs of the code for each participant to account for various sources of variance, including initialization and hardware fluctuations. The entry top 6 teams were run 9 times, and other teams were run 3 times. Larger error bars correspond to code failures, for example, out of memory. Such failures did not occur for the 2 top participants. The challenge was designed to induce participants to address a number of questions. So, do the results of the challenge answer those questions? To answer the first question, regarding whether a unified approach emerged across modalities, we surveyed the top-ranking participants of the AutoDL challenge. Unfortunately, 100% of the participants used different approaches for the different modalities. So there is still much work to be done in this direction of research.